The next time it rains, look closely, not at the puddles, not at the sky. Look at the rain itself, the individual drops falling past a window or a street light. Some of them are tiny, barely visible, drifting like mist. Others are fat and heavy, hitting the ground with a sound you can actually hear. They all fell from the same cloud. They all started as the same water vapor. So why are they so different? The answer involves physics, fluid dynamics, atmospheric science, and a shape most people have been imagining wrong their entire lives. Because the raindrop you picture in your head, that classic teardrop shape, doesn't exist. Most people, if asked to draw a raindrop, would draw the same thing, a round bottom with a pointed top, like a tiny falling tear. That image is everywhere. It's on weather apps. It's in children's books. It's on umbrellas. And it is completely wrong. Real raindrops don't look anything like that. Their actual shape changes constantly as they fall. And the reason why tells us something remarkable about the invisible forces at work in the air around us every time it rains. Understanding why raindrops are different sizes means understanding a story that begins inside a cloud, travels through thousands of meters of turbulent atmosphere, and ends the moment a drop hits the ground. A journey that takes less than a minute but involves some of the most fascinating physics on Earth. Let's follow that journey from the beginning. Stage 1. Birth inside the cloud. Every raindrop begins as a microscopic water droplet, so small that thousands of them could fit on the head of a pin. These tiny droplets form when water vapor condenses around dust, pollen, sea salt, or other microscopic particles floating in the atmosphere. At this stage, all cloud droplets are roughly the same size, incredibly small and nearly weightless. Air currents inside the cloud keep them suspended, floating, constantly moving. But they do not stay the same size for long. Stage 2. Collision and coalescence. Inside a cloud, these microscopic droplets are in constant motion. They collide with each other. And when two droplets collide, they sometimes merge, combining into one larger droplet. This process is called coalescence, and it is the first reason raindrops end up different sizes. Not every collision results in a merge. Sometimes droplets bounce off each other. But when merging does happen, the new droplet is bigger, and a bigger droplet moves differently through the cloud. It falls slightly faster, colliding with more droplets, merging again, growing further. The process accelerates. Some droplets get lucky, colliding and merging many times, growing large enough that the air currents inside the cloud can no longer keep them suspended. Those are the drops that fall. Others merge only a few times, remaining small. Those fall too, but as smaller drops. Stage 3. The fall. Once a droplet leaves the cloud, the real transformation begins. A falling water drop is not in a vacuum. It is moving through air, and air pushes back. As a drop falls faster, the air resistance pressing against its bottom surface increases. A very small drop, less than about 1 millimeter, falls slowly enough that surface tension keeps it nearly spherical. It looks like a tiny perfect ball. A medium-sized drop, around 2 millimeters, begins to flatten slightly on the bottom as air resistance pushes upward against it. A large drop, 3 to 4 millimeters, becomes significantly flattened. Its bottom surface is almost completely flat, like a hamburger bun shape, while its top remains rounded. And a very large drop, approaching 5 millimeters or more, gets pushed so dramatically that it develops a concave bottom, like a tiny parachute. At this point, the surface tension holding the drop together is fighting a losing battle against the air pushing up into its base. Stage 4. Breakup. At around 5 to 6 millimeters, something inevitable happens. The air pressure pushing up into the concave base of the drop becomes too great. The drop destabilizes. Its base pushes inward, then outward, and it shatters. One large drop becomes many smaller drops. Those smaller drops begin the process again, falling, flattening, potentially breaking up further depending on their own size. This breakup is the second major reason raindrops come in different sizes. It is a physical size limit, a maximum diameter that a falling raindrop simply cannot exceed. Here's where the physics becomes genuinely fascinating. The shape of a falling raindrop at any given size is determined by a balance between two forces: surface tension and aerodynamic pressure. Surface tension is the tendency of water molecules to stick together. It is the force that makes water form spherical drops in the absence of other forces. Because a sphere has the smallest possible surface area for a given volume, minimizing the energy needed to maintain the droplet's shape. Aerodynamic pressure is the force of the air pushing against the falling drop. The faster the drop falls, and the larger its surface, the greater the upward pressure from the air it's moving through. At small sizes, surface tension wins. The drop stays roughly spherical. As the drop grows larger and falls faster, aerodynamic pressure increasingly wins. The drop flattens, deforms, and eventually breaks apart. Scientists have used high-speed cameras and wind tunnel experiments to observe this process in extraordinary detail. What they found confirmed something counterintuitive. The faster and larger a raindrop becomes, the less time it has left before it destroys itself. There is also the matter of evaporation. As a raindrop falls through drier air below the cloud base, water evaporates from its surface. Smaller drops are most vulnerable. In dry enough conditions, a tiny raindrop can evaporate completely before it ever reaches the ground. This phenomenon is called virga, rainfall that falls from a cloud but disappears before hitting the surface. But here is the twist that surprised even researchers who study this for a living. For decades, scientists assumed that the size distribution of raindrops, the mix of small, medium, and large drops in any given rainfall, was determined primarily by conditions inside the cloud. The type of cloud, the temperature, the updraft strength. Then, in 2009, a researcher named Emmanuel Villermo and his colleague Benjamin Bossa discovered something unexpected. They found that the size distribution of raindrops is not primarily set by the cloud at all. It is set by the breakup process during the fall. When a large drop breaks apart, it doesn't split neatly into two equal pieces. It shatters into a spray of drops of many different sizes. A few large fragments, many medium ones, and a cloud of tiny droplets. And those resulting drops, if they are still large enough, break up again and again. Each generation of breakups producing the same characteristic spread of sizes. The result is that by the time rain reaches the ground, the distribution of drop sizes follows a remarkably consistent mathematical pattern. Regardless of the cloud that produced them, regardless of the storm's intensity, regardless of the location on Earth, it is a self-organizing system. The rain sorts itself. So what does all of this mean when you are standing in the rain? The light drizzle from a gray morning sky is made almost entirely of tiny drops, between 0.2 and 0.5 millimeters, that barely disturbed the air on the way down. They drifted more than fell. The heavy summer thunderstorm pelting your umbrella contains drops ranging from 1 millimeter to nearly 5, constantly breaking up, forming new drops, a cascade of ongoing physics happening above your head at every moment. The mist you walk through sometimes isn't technically rain at all. It is fog. Cloud droplets so small they haven't grown large enough to fall, simply drifting with the air currents around you. And that teardrop shape that everyone draws, the pointed top, the round bottom, it has never at any point been the shape of a real falling raindrop, ever. Here's the thought that should stay with you. Something as ordinary as rain, something humans have experienced for their entire existence on this planet, contains physics that wasn't fully understood until the 21st century. The size of each drop, the shape as it falls, the moment it breaks apart, the pattern that emerges from millions of breakups happening simultaneously in the air above you. All of it is governed by forces so precise that the result is mathematically consistent across every rainstorm on Earth. The next time it rains, you are not standing in weather. You are standing inside a self-organizing physical system, ancient, elegant, and still revealing its secrets. Look at the rain differently now.